Hey everybody, welcome to the afternoon session, or the last afternoon session on the second day of DataWorks. This is really exciting. We're getting a tutorial today on how to use Git from Curtis Miller. He's a research staff member at the Institute for Defense Analyses, and he's going to walk us through some of the basics of how you use this very powerful tool for version control and sharing. So with that, I'll turn it over to Curtis.
All right, thanks, Matt. Hello, everyone. I am here to talk to you about Git and how to use it, primarily with the emphasis on reproducible research. People in the software development community have been using Git for a very long time. It is very well known. It's one of the technologies that powers giant collaborations with hundreds of developers building applications such as Windows, and I'm not sure if Windows uses it, but they probably do. It's a very key tool to building some of the biggest programs that you're aware of. And we're going to talk about how we can use it for reproducible research. So we'll get started. We'll talk about briefly what Git is. We'll talk about what a repository is, a Git repository is, and how to make it. Long story short, a repository is a collection of files. We'll talk about how we can track data using Git. We'll talk about how to make a Git branch, and then we'll conclude. To get started, Git is a powerful and popular open source version control system. Version control software manages changes in files as those files are edited over time by one or more users. With Git, you can track the changes that you make to your files, or you can control multiple versions of your files simultaneously. So if you have version A versus version B, or Tom's version versus Matt's version versus Cynthia's version, Git will keep control of that and make sure that all of those different versions of your product are handled in a sane way. So to get started, the first thing you need to do is get it onto your computer. Git is free. It is open source. It is basically the de facto version control system. There are other systems out there, like for a long time, SVN was a common version control system. And there's nothing wrong with SVN, but we're talking about Git today, and I would say that Git is probably the more popular tool. So here's a link where you can go to get onto your computer. We're going to be doing this tutorial in Windows, but I hope that a lot of the principles that I talk about will carry over to Macs and Linux, because it works for pretty much every operating system. So on Windows, in order to when you install it onto Windows, Git is going to install a couple things: a graphical user interface, or GUI, and also a bash terminal. So those command lines where you type commands into and it does things, it's going to install that. What is one way you can open up Git on your computer after you've installed it? You can right-click on the folder where you want Git to work in, and when you right-click on it, you're going to see a menu, and that menu should have a couple new options to it. There's going to be the Git GUI and Git Bash, so it'll say Git Bash here. So for this tutorial, you're going to click Git Bash here. So on Windows, it's coming with Git. When you install Git onto Windows, it's coming both with a graphical user interface and the bash terminal. The GUI may be user-friendly, but to be completely honest, I think if I've ever opened it, it was by accident. I have never really opened it intentionally. And if you're looking for help on how to use it, or if you go onto the internet and ask people, how can I do this in Git, they're probably going to tell you some command line commands. So for the most part, I'm going to focus on the Git command line, but the concepts from talking about the command line should carry over. Ultimately, the graphical user interface is running the command line in the background. So that's what I'm going to focus my attention on. Another thing is I'm going to be using a website called Github to kind of demonstrate some of the features where you can do collaboration with Git and what that kind of looks like. So I had to have a GitHub account, which you can get one for free. I think if you get one for free, though, you're going to be making primarily public repositories, so keep that in mind. So the first thing we need to do with Git is we need to give it some basic information about ourselves. Right now, we are looking at a bash command line. Very shortly, bash is not Git. So this program we're looking at is what's known as a shell. A shell is a program that runs other programs. And in this case, the program we're running is Git. But let's kind of dissect what it is we're looking at right here. That green text that we're seeing is basically saying who you are and what computer this program thinks we're on. The yellow text is telling us where on our computer we are. If we kind of go back here, we look at this window here with our folders, you can notice, okay, it looks like we're in this folder Miller Curtis G. That's my home folder. And there's another folder inside of that called development. And then within that folder, development, is another folder called Git. And that's kind of what this yellow text is saying. You're in that Git folder inside of the development folder inside of your home folder. And all of that together, it serves as a prompt where you're going to type in a command. So you type in a command and you press the enter key, and then that command runs, and there may be some output from that command that's going to follow. So let's talk about the commands that we started with. The command we're looking at right now is git config, which is a way to give some configuration settings. These are your options, you might say. So the first command we're running is git config global username Curtis Miller. This is just telling Git what my name is. So the first command tells Git my name. So the command is git config. Global is an option passed to that command saying that this is going to globally apply for my computer. This is like setting it for whenever I open up a terminal again. So you're only going to do this once, right? Then we have the option I want to set, which is my username. And then in quotes, I put my name, Curtis Miller. And the reason why I put it in quotes is to make sure that it actually captures like that space in my name, because otherwise it'll think that those are two separate things. So you're basically saying treat my name as a unit. The next command is git config global user email cmiller@ida.org. So now I'm telling it my email. This is going to matter later. And if we were to run those two commands but not actually provide it a name or provide it an email, it would just tell us what our current settings are. So it just spits out your name is Curtis Miller, this is your email, this is how you can see what your current settings are. Do this once, ever, or at least for a computer, and you're good to go. So, okay, that was very interesting. I want to learn more. If you want to learn more, every Git command has a help page. How do you get help? Type in that command and then type -- help. And what will happen is on Windows, a browser will open up with a manual page that will give you a description of that command. This manual page may be dense, especially if you're getting started out with Git. So I would have in mind what it is you want to do and what command does it. And once you open up that command, I would go scanning through that page to look for an example of what it is you want to do, and then try to imitate that example. But you have some manual pages available to you. Pet peeve of mine is people thinking that Git is GitHub. Git is not GitHub. Git is its own thing. GitHub is a hub for Git. It's where people store their Git repositories. So there are these various websites, GitHub, Bitbucket, GitLab, that serve as a way for people to collaborate using Git. But Git is its own thing. You have it on your computer. It doesn't require an internet connection. I've run Git on my own computer for my own projects without ever uploading anything to a server. And by the way, this also means that for your classified networks, you can still use Git because it doesn't actually require a server to anything. You just are running it on your computer, and it's keeping track of what you're doing. Okay? So next up are repositories. What is a repository? It is a collection of files that Git is tracking. So Git is going to track the history of these files and the differences between these files across time and between different versions or branches, right, where you can branch out your files for different users or to try out different ideas for different purposes, maybe different products that you're going to deliver that are mostly the same but slightly different. Git will keep track of that in a repository. I would say that a repository should contain an entire project. So everything that is relevant to that project should be tracked in the repository. So it should be self-contained, right? Now, admittedly, Git is, you're not going to be, if you're doing a lot of your work in R, you're not going to put R in your Git repository. Right? But if you're writing any sort of scripts that are supposed to go with R, that are what you execute in order to do your project, then those should be put in your repository. It should be self-contained. Anyone who wants to run your project should be able to just download this repository and run it. So if you want to share your project, you're going to share this repository, or you may share a link to this repository. And in terms of what a repository is, it is a folder on your computer with files in it. That's all it is. But you've kind of added some extra stuff into that folder that's going to make working with it easier. And sharing with it, tracking stuff in it, is going to make it easier. There are many websites that will host repositories. IDA has an internal Bitbucket. We're going to focus in this tutorial on GitHub, which in retrospect was a mistake because we use Bitbucket, but oh well. We're going to go to GitHub. I already have a GitHub account. So on my main page on GitHub, I want to create a new repository. There is a button up here where you can click that will make a new repository. So I click that button, and it gives me this form that I now need to fill out. So I need to tell it the name of the repository, something to keep in mind with repository names. Don't put spaces in that name. Git is not going to allow you to do that. So if you want to separate out words, you can use underscores or you can use hyphens. Give it a description of your project, what it's about, so that when people are looking for projects, they can find your project. Tell GitHub whether this is a public or private project. And also, GitHub gives you the option to initially populate your project with some files that are usually showing up in projects. So in this case, we start out with what's known as a git ignore file. We'll talk about that later. And also a license, which is supposed to describe the terms under which this software is supposed to be distributed. Yeah, we just create those and then click the button at the very bottom to actually create the repository. So then GitHub is going to take you to this page where you can now see your repository. And from looking at this page, we can learn a lot of things. We can, for example, if right now we see ntguardian/datahubworks22 git intro, that is basically the name of the repository on GitHub. So it's associated with my username and then the name of the repository. That's how GitHub keeps track of repositories, by who owns them and what they are. There's going to be some files in this repository initially, and you can click on those files to view them. There is a button that corresponds to what branch of the repository that we're looking at right now. Right now there's only one branch, the main branch. But we'll talk more about that later. And also at the very top of the repository in your browser is going to be the URL describing where it is on the internet this repository is being kept. That's going to be important if you want to share it. Let's suppose we click one of these files. In this case, I clicked on the license file. What are we looking at? We can see what file it is that we're looking at, including what branch, what version of the file that we're looking at, who has been working on the file, and any sort of recent activity. We can click on a button to see the file's history, and also we can see the file's contents. This is a plain text file. A plain text file is basically a file that you could open up in Notepad and understand what it says. Or maybe you don't understand it, but it looks like someone else could, right? So it looks like someone who knew what the file was could probably understand it, as opposed to, say, a binary file where if Notepad allows you to open it up, it just looks like gibberish. Pure, utter gibberish. Right? It doesn't look like it makes sense to anyone except a computer. So that distinction is rather important because Git really likes plain text files. So knowing what is and isn't a plain text file is going to be key to use it. All right, so right now this repository is on GitHub. We need to get this repository onto our computer in order to do anything interesting. There is a button that you can click, the code button. So click this to open up a dialog that then offers you a URL that you can copy so that you can then clone it to your computer. So in that Git folder, I think I have my, oh no, I don't. Okay, so in that folder Git, I run this command Git Clone, which is going to clone it to my computer. You're going to do this once when you get this project. And then you put in quotes, you're going to paste in the URL. And by the way, a tip, when you paste in this terminal, don't press Control V. That doesn't mean paste. Right click and then click paste, right? That'll work. If you do it the other way, then you might end up with, you might wonder why your command didn't work. And I don't want to explain it. So anyway, I would also put it in quotes. I don't know that this is strictly necessary, but I know that it will work if you put it in quotes. All right, so then it will copy it to your computer. Now it's on our computer. It is a folder in our computer. It also puts out some output that basically says I'm downloading this project and then I'm all done, right? And then it waits for your next command. When we go into that folder, we can see some of the files, well actually all of the files that we saw on the website, but also an additional folder, .git. That folder .git is what Git uses to do its magic. Don't ever mess around with that folder, just leave it alone. It's for experts only. So just know that that folder is actually what Git is using to do its work. All right, so that is, in short, how you make a repository on GitHub. I actually didn't have to use GitHub for any of this. I could have just had a folder on my computer. Maybe it's populated, maybe it isn't. And inside of that folder, I type Git in it, and now Git is tracking. Right? Git has gotten started. That would be like if you wanted to do your work on a classified network and there isn't an external place for Git repositories, then that's probably what you're going to do. You would use the Git init command. So just say, start tracking stuff. Okay, so that was how to make a repository. Next up, we need to start tracking some data. The way Git tracks data is via what are known as commits. It's the basic unit by which Git is tracking your files. It is how you're going to go back to previous versions of your files. You're going to go to previous commits. So what you do is you add files to a commit saying this needs to be tracked in a commit. Then you make the commit where you officially say track the changes to these files, and that's it. Those files have now been tracked. You now have like a timestamp of those files, right? So for the text files that I said are very important, Git's not actually copying the files entirely to do its tracking. Instead, what Git does is it tracks how the files changed. It tracks changes only. So it tracks the difference between that version of the file and the next commit. And if you ever want to get a previous version of those files, you're going to check out a previous commit to recover those files. I like to think of using Git like belaying while mountain climbing. So what you do when you belay is there's a rock climber, and that's you, the programmer or the author, whatever. And Git is going to be the person holding the rope. And as you're climbing up the mountain, Git is going to be keeping that rope taut and tracking your progress so that if you fall, you don't fall 100 feet to the rocky ground. Instead, you just fall a couple feet to your most recent commit, at which point you can reorient yourself and get back to work. Right? Or if you ever need to, for some reason, go back down the wall, Git can let out some rope to get you back to your previous point, and you can start from there again. But it's going to keep track of your progress as you go on. And this is going to have a few benefits for you. For example, if you make an immediate mistake, you can undo it. If you made a mistake several weeks ago or several months ago, you can go back to when that mistake was made, maybe figure out what you did wrong, and then fix it. If you deleted a file that turns out to be important, you can get it back, which, by the way, also gives you permission to delete your files if you don't think they're important anymore. You can just delete it because Git has a record of that file. You can create branches where you can try stuff out in this branch. I have right now a branch that I know is stable, so that's going to be my main branch, but I want to try out this crazy idea. So I'm going to make a branch, make all sorts of edits that I want, and that's fine. Because if I ever change my mind, I can go back to the main branch, Or if I like my changes, I can merge those changes back into the main branch. So this is a way for you to have multiple versions, maybe for experiments, maybe for multiple similar products, or maybe just so that you can have multiple collaborators working on the same thing without stepping on each other's toes. Okay, so let's start tracking some changes. And the first thing we're going to do is make a README file. This was a file that GitHub offered to make for us, and really we should have such a file, but I decided to make it by hand. So this is actually RStudio that we're looking at here, but you don't need to use RStudio to use Git. You could use Notepad if you wanted to. Just use a plain text editor, not Word, just a plain text editor. So in this case, I write a file, an R Markdown file, which is using the Markdown syntax. I'm not going to talk about that today. It's just a way to kind of say this is a header, this should be in italics, stuff like that. It's a way to format your stuff. But it's just a file that's describing what is in my project, what people should know about it the moment that they look at my repository. And actually GitHub and a lot of these Git repo hosting sites are actually looking for a README file so that they can render it nicely for people and show it to them. And that's a way for you to advertise what it is that you've made and what people should know if they're going to use it. So I wrote such a file and then I saved it in that repository, in that folder. The thing though is Git doesn't know yet that it needs to be tracking this file. Just because it's in the folder doesn't necessarily mean that Git is tracking it. So we need to add it to the next commit we're going to make. How are we going to do that? The first thing we're going to do is use the command Git Add. So in this case we say Git Add and then the file's name, readme.md. I wrapped the file's name in quotes. I probably could have gotten away without doing that, but I would not have gotten away with it if I had put spaces in my file name, which, as a tip, I would rather that you not put spaces in your file names because it actually makes them rather hard to manage in environments like this. Because you have to be very careful about your quotes in such instances. So please don't put spaces in your file names. It causes headaches. So in this case, I just say, this is the file I want to add. Okay, Git is now ready to add that file to the commit. But we haven't actually done the commit yet. This is a way for us to maybe make multiple additions, and as we make those additions, we add them to the next commit. And then once we're all done and we're ready to go, we then type git commit, which is the next command, and then we add the option -m, which means we're going to have a message associated with this commit. That message is going to be a signifier to someone else who's reading through these commits, and maybe it's yourself in the future, telling them or you what you did, what this commit does. So in this case, my message is I added a README file, and this file is going to describe the purpose of this project. So you write that message in quotes, and then you hit enter, and you now have a commit. You've made your first commit. So that's great. You now have a save point where you made this README file. The thing though is, this is on your computer. It's not on GitHub. If you were to go look at GitHub at this point in time, you would not see these changes. So we need to let GitHub know that we made those changes. And for that, we're going to use, in order to communicate with that server, we're going to use a couple commands, Git Push and Git Pull. So imagine there is a host server that is supposed to be hold the authoritative source of this repository where you have your local copies, but this is like the authoritative copy. This is the one that everyone has in common, that everyone communicates with. So that's going to be on the host server. In this case, that host is going to be GitHub. And to push the changes that I made, in order to share those changes with others, I need to push it to that repository. The command for that is git push. Push it to the repository, communicate those changes to everyone else whenever they decide they need to get those changes. If I want to get the changes from that host repository, I use the command git pull. That pulls those changes from that server to my computer. And now I have a copy of what should be the most up-to-date public copy of this project. So this is something you could be doing if, I guess you could be doing this if you had this project on multiple computers where you're kind of using GitHub like Dropbox. If you're familiar with Dropbox, it's just a way to kind of share across computers without using a thumb drive. I mean, that would be how you're getting files to and from multiple computers. But if you were doing, if you're involved in some big collaborative effort, this would be a very key part of the process. In fact, this is how those companies with hundreds of software developers or thousands of software developers working on one product are managing that collaboration. And in this case, and probably for most reproducible research cases, this is pretty simple. Maybe there's like 5 people working on this thing. But actually that process of pushing and pulling, that's a rather involved process because Git's not just dumbly accepting or rejecting or giving out changes. If you were to actually do a push in a rather complex project where you are out of date, Git would actually recognize that you are out of date and reject your changes and say you're out of date. Get the most recent version before you tell me what you did. So it's actually, it's a rather involved process, but in this case, it's probably going to be rather simple. Okay, so in order to get our changes to that website, we need to push them. The command is git push, although in this case, it's not quite that simple because this is the first time we're pushing, and GitHub is going to say, who are you? So you need to let GitHub know that you have permission to start pushing stuff to this website. So you do git push with the option U, so git push -U, in which case it's going to open up this interface where it's going to start going through this process of authorizing you to make pushes to this repository. Follow the instructions, and eventually you'll reach this point where the push goes through. It says that it does a bunch of things where it's uploading your files, and then it's like, okay, everything's good. You're up to date. And then if we were to go to that website, this is what we would see. Notice now that there is an additional file on this page, and there is a message that is associated with that file, which is the most recent commits message. It says how that file has changed most recently. So in this case, we say we have a README file, and we added it, right? So that message appears, and as I told you before, GitHub actually looks for this file, so it actually renders it nicely for people when they go and look at your project. So there's a whole bunch of stuff we can see. All right, that's cool. Let's make some more changes. In this case, I'm going to do some statistical analysis that's basically an exercise from a book I found on generalized additive models. So I make a folder called vignettes, and in that folder I create an R Markdown document. R Markdown is a popular format for reproducible research. I think we had a talk on reproducible research here. So you type out your analysis at the same time as you do the analysis. So you write what you did in addition to the code, right? So you're writing your report at the same time as you do the computations in it. Okay, that's all rather lovely. That also is a plain text file, so I save it in that folder vignettes. And yeah, also in addition to that, I changed that file readme.md, where instead of having this very short text, I added some more lines kind of describing what it is I was doing. Okay, long story short, I made some changes. I added some files. I added some lines to files. We need to track that. How are we going to do that? We're going to do, in this case, I could do Git Add and then list out the files individually. Or I can say Git Add all, add everything. So Git Add -- all, that means anything I changed, any new files, any files I deleted, add them all to this commit. Then I say git commit -m, my message. And that's like 90% of the Git workflow right there. Git add, git commit, git add, git commit. That's most of it right there. Every once in a while, you want to share your stuff with other people, in which case you'll write git push, and then you go about your day. So, and yeah, that's pretty much it. That's most of what I do. So some thoughts on committing. When should you do it? Because you might be thinking, okay, git commit. Should I commit every single line of code that I add individually? Probably not. That's probably excessive. Should I wait 5 months and add several different files and have 90 new functions and commit it all at once? No, probably not. That's not a very useful breakpoint. So somewhere in the middle of those two extremes is going to be the happy place. I would say anytime you make a significant change where it's like, I'd like to be able to return at this save point, you should make a commit. You're probably going to be making a commit at the end of the day, I would say. It's like, all right, I'm done for the day. I've done some interesting work, so I'm going to make a commit. I would not worry too much about saving space because, like I said, Git only tracks changes. It doesn't copy entire files. Well, if they're text files, it won't copy the entire file. It only tracks what's different. Okay, so I made some changes and I pushed it to GitHub, and notice in that case I didn't have to do the -u. I just said git push because GitHub is like, okay, this guy's cool. So now we go to GitHub and we look at what we did. A number of things have changed up to this point. Notice that the message that was for that most recent commit is now at the top of the page. Instead of having one commit as we started out with, we have 3 commits. Those 2 files, git ignore and license, they still have the same commit that we started out with, because they haven't changed at all, right? So Git hasn't changed them, but this Readme file, it has the most recent commits message because it was altered in that commit. There's also a new folder with the new files. We've also updated the Markdown document. So yeah, a few things have changed up to this point. Let's start. There's some other things to note. For example, you can click on that line 3 commits right there. That's how you could see the history of this project on GitHub. So that's what you would click to see the history. And there's another thing right there that you see these 7 characters, 0f66, I don't know, some gibberish. Those 7 characters are the first 7 characters of a long string of characters that uniquely identify that commit. It's known as the commits hash. That's how it Git identifies it. Those are the first 7 characters because you are allowed to abbreviate hashes.
First or the last?
First characters. So, and I'll show you the full hash in a second. Let's actually go ahead and click that 3 commits button. This is what we would see. We would see that first commit. And so we see the commits. We see when they were done. And we also see the messages associated with them. So this is a way to kind of see the history of this project. We see who made those commits. Notice in this case, there's actually 2 authors. There's ntguardian, my username. And there's also that name that we put in our configuration settings. There's also we also see a couple buttons. One of those buttons has those 7 characters, which is supposedly uniquely identifying the commit. And there's also these 2 angle brackets. If you were to click the angle brackets, you get to see what the entire project looked like at that time, right? Whereas if you click on that hash, or the part of the hash, you would see what changed in that commit. What were the changes that you made? And by the way, nothing that you're seeing here is unique to GitHub. Yeah, I'm showing it on GitHub, but Bitbucket would show you the same thing. GitLab would show you the same thing. And for that matter, Git would show you the same thing. You don't need GitHub to do this. You can go to Git and type in git log, and it actually would show you a log. In this case, it actually does show you the full hash that is associated with that commit that identifies it. That's really long, but the good news is that you don't need the whole thing. If you abbreviate it with the first 7 characters, that's usually enough. You could even probably do it with 4. Like 4 characters would probably be enough, but you are allowed to abbreviate that thing to as much as you need to uniquely identify it. 1 is probably too few, but 4 might do it, and 7 probably will. You can see the messages. You can see who made these commits. There's a lot that you can see here. It should be noted that in this case, this project was rather short. There's only 3 commits, so this was able to fit on 1 screen. If it didn't fit on 1 screen, then Bash might use a program called less, or maybe it's more. I don't know. Less is more. But it would use a program to kind of allow you to scroll through this message. And you could press the up key to scroll up, the down key to scroll down, and then when you were done, you can press the letter Q to quit. But that might be something that it uses to display these messages for you in case it doesn't fit in one screen. Just know once you see something like that, press Q to quit. That was all rather verbose. If we wanted, we could abbreviate it by passing some additional options to that command. So in this case, the graph option, the one-line option, the decorate option, and the all option. And that would kind of create an abbreviated history of this project where it's showing you only those first 7 characters and also the message. In this case, our project is rather simple. There's not a lot of branching going on, but that also would be displayed in this graph. So it looks rather simple for now because our project only has 3 commits and they were done in order, but it might get more advanced if your project had advanced branching going on. Anyway, so that's kind of looking at the history of this project. What are we looking at here? Very briefly, if we had clicked instead that hash, those 7 characters, we would then see what changed in the commit. So this is a display on GitHub that's showing us the changes that were done. Git thinks in terms of lines added and lines removed. So if you make any change to a single line, then Git will say, delete the old version of the line and add the new version. So it thinks in terms of different lines. Lines that were deleted are shown in red. Lines that were added were shown in green. New files are all new lines, so it's going to be all green. Similarly, if you deleted a file, then all those lines were deleted, so all red. And once again, we see that identifier for the commit. There's also some characters around the top that kind of show you where in the file you're looking. So about what lines these changes happened, if you want to go find it in the file for some reason. So, okay, this is rather nice. Do we need GitHub to see this information? No. We can. This is what's known as a Git Diff. And we can look at diffs on using Git itself. So Git Diff actually is a rather general purpose command. It's going to show you not just the difference between this most recent commit and the one right before it, but this commit and the one 7 months ago, or my version of the project versus Dan's version of the project. It's a general purpose command to show you how things are different between different versions of this project, either across history or across branches. So that's the command. In this case, if I want to see the difference between the current version of the project, or the version that I'm looking at, signified by head, and the one right before it, which is head tilde, I would type in this command. And then in that terminal, I can see what the changes were. And similarly, things that were added are shown in green, and things were taken away are shown in red. You might be wondering, wait a minute, why is it adding a line that has merging in it and taking a line that has merging in it? Like, aren't those the same? Actually, they're slightly different. You just can't see it. There is a new line character at the end of the green version that wasn't present in the red version. So Git ends up deleting the whole line. Don't worry about that. Git took care of it. So, and again, if this was too long to fit on one screen, which can very easily happen, in fact, that's the case here because there's several files with lots and lots of lines. Again, that program is going to be used where you can press up to scroll up, press down to scroll down, or press Q to quit. So, but that's a way you can look through the changes and get a summary of what's changed. Well, not a summary. This is all that changed. Okay, that's looking at how everything in the project changed. If you wanted to see just how one particular file changed, you just type in the file's name at the end of that command, and that will show you how that specific file changed. Okay, so we can see a broad history of a project. We can see how a project changed in commits. What about just seeing what the project looked like at a particular point in time? Well, if you were to click on those brackets that we saw before, those angle brackets, this is what you would see. This is what the project looked like at the time of that commit. Notice that instead of saying main up there in that button, it now has that identifier for that commit, saying this is the commit that we're looking at. This is what the project looked like at that time. If we were to click on that button, it would open up a menu, and then we could click main to go back to the most recent version of that branch. We didn't have to use GitHub to do that. In fact, we often won't want to use GitHub for that because it's nice to see it, what it looked like on the internet, but it also should be something that we can use on our computer. Right? If I want to rerun an analysis, I should be able to do that on my computer. So what I use to get that old version on my computer is git checkout. So that checks out, in this case, an old commit, but it will also check out branches. It can also check out a file from an old commit. It's a general purpose command that gets old stuff for you. So in this case, I check out a whole commit. That's the idea of the commit that we're checking out. And by the way, this is changing the files on your computer. Now, I think this command is safe in that if you made some changes and you do git checkout, I think it will actually hold back and say, hey, you made some changes that I'm not aware of. I'm not going to check out until you do something about that. So I think it is safe in that sense. So just be aware that that's a thing. Also, maybe you haven't really been paying much attention, but there's a little bit of blue text after that yellow text. Starts out by saying main, and then at the bottom down there, after I do that checkout, it changes to that string. And that's kind of the command line's way to give you a hint at what you're looking at on your computer. Right, so once it changes to those characters, it's saying you are now looking at that commits version of your project. Right? So that's something to kind of pay attention to. That command line is trying to help you in terms of interpreting what it is you're looking at. And yeah, if we were to actually open up our project in Windows and look through the File Explorer, we see that things have changed. That one vignette that we had in the vignettes folder, it's gone now. Our README file is what it used to be. So everything is as it was before. Things have been deleted because they weren't present in the project at that time. So how do I go back to my most recent version? I just type in git checkout main because that's the name of the main branch. So I just check that out and I'm back to where I used to be. And notice, by the way, that blue text changed too. We're back to where we used to be. Okay. I actually only wanted one file from that commit, supposedly. So in that case, I just say git checkout, the ID for that commit, and then the file I want. And then it gets that old file. So now we're back. Git reset hard. I'm going to talk about that next. Oh no, I deleted an important file. I want it back. Well, I can reset my project by running that command git reset hard, and it will restore my project back to that old commit. So this is like I slipped on the rock wall and the rope catches me. Oh no, I made some changes and they weren't very good. I want the old version back. Git reset hard. It restores your project back to that old commit. Now wait a minute, it didn't look like a lot of questions were asked. Does that mean that if I made some changes that it would have deleted them even if I wanted to keep them? Yes. It would have deleted everything. It will go back to the way it was before. So this is kind of a panic button, or maybe something where you're fully aware that maybe you're doing some experiments and you know that whatever it is you're doing, you're not going to want to keep it, right? So you're going to very quickly reset, but just be aware this will delete everything and it will not ask you whether you want to do that. It will just do it, right? So this is the only warning you will ever see before you lose your work. Okay, so this all up to this point should be some indication. I'm doing really well on time. This should be some indication that your workflow based off of using Git is going to change. So one thing that you're going to want to stop doing is trying to bootstrap your own version control by changing the names of your files. So in this case, like a common trick is to associate that file name with the date on which it was made. This is cluttering up your project so that if anyone wants to understand the structure of that project, they have to go scrolling through a whole bunch of files that don't matter. So it makes your project harder to understand. If you wanted to get an old version of this project, you're going to be looking through these file names. And by the way, there is nothing that stops me from opening up one of these files, making a change, and then saving it, in which case that file name is now a lie. And by the way, if you look at the timestamps for those file names, it's already a lie. So none of that really is really meaningful anyway. So there's zero protection in terms of actually keeping this the way it was at that time. And think about what you would want to do. I guess this would be okay if this were the only file that you cared about keeping a record of, ever. But at the same time, that's not really how projects work. Usually a project has multiple files that are informing other files. Like there's the data file, there's the files that were involved in the analysis. There were several data files, and there's also the report. So there's a whole bunch of files that exist at any given time that basically describe the state of that project. So really, you're going to want to get all of the files at that given point in time. And like if you wanted to reconstruct what the project looked like on September 7th, 2021, you're going to have to find which one of these was active on September 7th. By the way, the file name is a lie. And you're going to have to do that for every single file that matters to that project. That sounds like a lot of work. And thankfully, with Git, you don't have to do this anymore. Because Git now has a record of your files. It is doing that automatically. If you want the old version, you Git checkout, and it will get the old version for you. And it will do so in a way where it's like, this is what the project looked like at that time. So you don't have to do this anymore. By the way, the person who I'm shaming here is me. Okay, I'm the one who did that. Same thing here. I'm the one who did this. Another pattern that I kind of see, and like I said, I've done this before, when you're doing your code, you don't want to lose the old version of that code because there's something interesting about it, but that's not the version of that code you want to use anymore. So you've modified it in some way. So you comment out the inactive lines. You don't have to do that anymore. You just delete them. In fact, you should. Because if those files are irrelevant to how that function worked or how this analysis works, then they're clutter. And you should delete them because they're just making your project harder to read. So by deleting them, you're making your project easier to read. And you don't have to worry about whether you're going to get that stuff back if you need it, because Git has a record of it. So you can get back the old stuff if you need it. By the way, both of these things, there were very admirable and desirable things that you were trying to do, which is keep a record of old files, keep a record of what you used to do. It's just Git is now doing that better, and it's doing it in a systematic way. Using email to manage collaborations, sending files back and forth via email messages. It's rather ad hoc. It is. If there really was only one file that you were ever editing, I guess this is okay. But as I said before, that's often not the case. Often there are multiple files that are being managed, that are being referred to at any given time. And think about how you would share this with a new person. Are you going to send them all 500 emails that you've been emailing back and forth? If they wanted to have the history of that project, are you going to send them all those emails? No. And by the way, here's how you would do it in Git. So I have a collaborator, they're an imaginary friend, and they did some changes, and they pushed them to GitHub. I now need to get those changes myself. I can see that they're on GitHub, I can see that some changes were made, and I now need to get up to date. How am I going to do it? I'm going to type git pull. I'm done. I'm up to date. I have everything that has ever been done. Git summarizes what changed, and now my project's up to date. I can see on my computer what they did. They added some lines. They did some of the work that was part of the project. So we're all good. So in terms of pulling, like pushing, you're going to push whenever you need to share results with someone else, or at least at the end of the day. And similarly with pulling, you should probably pull in the morning, or you pull whenever you need to get someone else's work. So just pull whenever you need other people's stuff. But that's how you keep up to date. Okay, so this was an R Markdown file, and one of the nice things about R Markdown is that it creates multiple versions of reports. If you want an HTML version to share on your website, or you want a PDF version that you want to print out, or you want a Microsoft Word version to share with the editors, you can make that with R Markdown. That's an R Markdown feature. I'm not really talking about that. But in this case, I generated a Word file from that R Markdown file. And that shows up in my folder. There's now a Word file in there associated with that R Markdown file. So we should track that in Git, right? No, we should not track that in Git. There are reasons why we would not want to track files. Things you should track: plain text files, TXT, R files, R Markdown files, PI files, TeX files, whatever. Git really likes text files. Binary files, not so much. So with plain text files, Git is tracking those changes, and we were able to see those changes when we were looking before. With the binary files, it's going to track the whole file, so it's just copying the file over and over again. Is that the reason why we're not keeping this file? No, that's not the reason. And to be fair, there are I'm saying avoid this, but I mean, if you can find if you absolutely must track a binary file, it's fine. It's probably fine. And I do it. I have no problem with tracking a binary file. But the real reason why we shouldn't track that file is for the second point. It is a file that was generated by another file, right? So files that you edit directly are the files that Git should track. A file that is a direct result of running another file, where you don't do anything to it. You just run another file, and this is what comes out. Don't track that file. It's redundant, right? So you shouldn't have redundant files in your project. In fact, all that's going to happen by tracking that file is Git's going to trip over itself if for some reason something changed, and it's just something that is irrelevant, that is redundant, and it's just an opportunity for Git to complain, really. Everything's been running smooth so far, but not everything will run smooth all the time. And I have had situations where there were some files that were being generated by other files, and we were trying to do some merges of our work, and it was causing problems because those HTML files that were being generated by others were different for some reason. And the worst thing of it all is it doesn't really matter, right? So really how the project should be working is when you share your repository, the person on the other side should generate the results themselves. So they should be the ones that click that button that says turn it into a Word file. Right? So they do that, not you. Right? So share only the stuff that is necessary to generate the files in the report, not the results themselves. Now, I made exceptions for this myself because I was using Git for my my grad thesis work, and I was doing simulations that were taking weeks to run, right? I really don't want someone else to have to do that. In fact, it wouldn't work because it takes weeks to run on the supercomputer, let alone what it takes on my laptop. So that's fine. And in fact, for that matter, if there's a reason to break any of these rules, then break it. Right? If there's a good reason to break it, then break it. It's fine. So if it's an essential file that's really hard to generate, go ahead and track it. Avoid irrelevant files. Why would there be an irrelevant file in your folder? Good question. Maybe look at yourself in the mirror. But actually, all right. So joking aside, though, like for example, if you're using RStudio, it might have an RHistory file, where it's like keeping a record of the commands that you typed into RStudio at the time, stuff like that. I've seen these irrelevant files show up because of what other programs are doing, the programs that you're using to do your work. But they're irrelevant. No one else needs to know that in order to be able to do their work, so you shouldn't track that file. So that should be ignored too. Now that said, if I type git add all, it will add everything, including the files I don't want to track, unless I tell it to ignore them. And that's where that file git ignore that we mentioned very early on shows up. This is a text file that you can edit where you can tell it, ignore these files. And you're not just telling it specifically to ignore a file, although you can do that. You can say, ignore that file with that file name. But actually, you can type in patterns that indicate what files you want to ignore. Like for example, you can say ignore any file that ends in rdata, or ignore any file that ends in tar.gz. I'm not going to go into too much depth on this. How it is that you generate these patterns, these are regular expressions. Regular expressions are rather difficult. There is some documentation that you can look at if you want to get really clever. And I do encourage you to get really clever. It keeps things clean. What I really want to do right now is there is a pattern here where already it starts out with just ignore files that are in the vignettes folder that end in HTML or in PDF because that's usually a generated file. We're just going to add docx to that list. So I add this to my git ignore file, and then I make another commit. I do git add all. I type in a command called Git Status that tells me what Git is about to add to the next commit. So it says, I'm going to modify git ignore and this R markdown file, because actually that was edited. I didn't really show up, but it was edited, and we'll see what changed. But it's going to add those two files and not that Word file. That Word file isn't going to be added to this commit, which is what we want. So we make our commit. 2 files were changed, not 3. We push it to GitHub. We look at GitHub, we look in that folder, that Word file isn't in there, which is good because we shouldn't have been tracking it. When we look at the changes, it tracked all the other changes, but it didn't add that Word file. And by the way, that's what changed in the R Markdown file. It changed one line when I clicked knit to Word. RStudio did that automatically. So it's saying Word is one of the possible output formats. But notice how it did the change in Git. It deleted the old line and added 3 new lines. So, okay. That's how you do a basic tracking, change tracking. I guess I got 20 minutes left. Now that we've talked about how to track changes, I'll talk about branches. In many ways, this topic is focused on reproducible research. It is focused on reproducible research. I will admit that branches aren't as important to reproducible research as they are to software development where Git was primarily created. Because you can imagine in a software development setting, there's the version of the software that you're shipping to the public. There's the version that you're considering shipping to the public, but you're shipping it to some testers first. And there's like the version that you're actively developing, along with all the previous versions, these legacy versions of the product that you're also keeping track of. So they have much greater use for branching than we do, but branching can be useful if you want to try some experimental changes without altering your original work. It can be useful if you want to have different people working on this project and you don't want them all committing directly to the main branch. Instead, what you'd rather have happen is they work on their own individual branches, make all the changes they want, then you come together as a team and merge them so that you have some control over this process. So it is an important enough concept that even if it's not as useful in this situation, you should still be aware of it. So what are the branches that we started out with? We type in the command git branch, and on its own, that's just going to list out what branches are present. Right now, there's only one branch, the main branch. And that is actually the branch that we're working on right now. So what if I want a new branch? I use that command git checkout again, but I add the option B, and I type in the name of the branch that I want to check out. So in this case, the name of the branch is my username, to kind of indicate to anyone who's looking that this is my branch, this is the branch that I play around with. Right, so I'm basically making a personal branch. So it creates the branch and then immediately checks it out, and that is now the branch that you are working on, no longer the main branch. Notice that blue text over there on the right? It is changed to the name of the branch that you're working on. And if you were to type git branch again, it'll show you the list of the branches. There is now a new one, and it is my new branch, C Miller, and it's shown in green. It's trying to indicate that this is the branch that we're working on. So then I do a bunch of work. I make a whole bunch of edits to this file, and I'm adding those changes, then I commit them, and I add the changes and I commit them. And I think at one point I checked out an old version of the file because for some reason I needed it, and I didn't want to use git reset. I just checked out the old version that I wanted and just started working on that because I decided I didn't like some changes I made. So, but I just started making some changes, and all those changes are being made to that personal branch, not the main branch. So if we were to check out that main branch, nothing would have changed. It would have been as it was before I did all those edits. Also, our imaginary friend, our collaborator, they're also doing some work too. They pull from GitHub, they get up to date, they make some changes. Actually, they created their own version of this project, Prob 6 and 8, where they're like, okay, I don't want to just do problem 9 from this textbook. I want to do 6 and 8 as well. So they made their own version of it that includes a couple extra problems. They make some changes, they add those problems, and then they push it to GitHub. And by the way, if we make some changes on the main branch, we don't have to repeat them on those other branches. We can merge those changes back into that other branch. That's a way for you to maintain two products that are very similar to each other. Git will know what the difference is between those two things. So you can have like version A to be shipped to sponsor A, version B to be shipped to sponsor B, and you can edit only version A, and Git will know how to pass those edits on to version B. Right. So that's also a neat feature you can have. But our collaborator does some work, and then they want to push. They ran into a problem where they tried to push, and then there was a complaint that this branch was not on GitHub, and GitHub was not aware of this branch. So the good news is that Git actually proposed a way to fix that problem. It said, you run this command down here where you tell GitHub about a new branch that you're working with. Actually, that command is out of date. If you look at Git documentation, it says don't run that command anymore. But whatever, I ran it anyway and it worked. So, it still worked. I did what GitHub suggested, or not GitHub. I did what Git suggested, and I was done. So then we go back to the work that we're doing, and we do a Git pull at one point, try to get some changes. And a couple things happen. First off, when we do the pull, we're made aware of the existence of a new branch. So that's good to know. And also, Git tells us that the branch that we're working on, the C. Miller branch, it's not on GitHub. GitHub isn't aware of it. So if we want to make GitHub aware of that branch so that we can push it up there, maybe to, I mean, we're probably not sharing this with other people, but it'd also be nice to just back it up on an external server. This is the command that we can run to do that. I didn't run that command. I ran this command instead. But this is just another command that I can run to make sure that that branch is on GitHub. So now that branch is also there. Okay, if I want to see this new branch that this imaginary friend collaborator created, then I can do git checkout. So I do git checkout and the name of the branch that I want, and it gets the branch. Notice that the blue text has changed on the right-hand side. So that is now the branch that we're looking at. What changed between this branch and our personal branch? What's the difference between these two things? So if we use the command git diff again, anything that's in the branch on the left but not on the right will be shown as red as if it's a deletion, and anything that's on the right but not on the left will be shown in green as an addition. So we run that command, and now we can explore what the difference is between these two different branches of the project. Anything in green is in one version, not the other. I think the green is the one that we checked out, and the red is the version that we're comparing to. So it looks like in the first line of the word modeling was misspelled and the spelling was corrected, but it adds a whole new line. So one is a spelling correction. Some is some extra prose and some extra code that wasn't present in the original version. So we get to explore some of those changes, and then we're good. And if we wanted to, we could have seen, instead of like looking at the changes, but we could have just seen what files were changed. In which case we just use the name only option to see the files that changed and not what the changes are. Anyway, we looked at that branch. It was all very lovely. We go back to our personal branch, and we do some more work, and we add it, and we commit it. And now that we've made a number of changes, it would be nice if we could get those changes back into the main branch. So we're going to do a merge. And what you're going to do for a merge is you're going to check out the branch where you want to merge the changes into, and then you run the command git merge, naming the branch you want to get the changes from. What does that look like here? We want to merge the changes from our personal branch back into the main branch. So we check out the main branch, and then we use the command git merge, and then the personal branch. We name the personal branch. And that will automatically merge all the changes that we made in that personal branch back into the main branch. So now the main branch is up to date. A merger is going to be treated like it's a new commit, but because it is an important step in that project, that merger, we can look at the log and we can see how things have changed. In this case, the merge process was very smooth. It was very easy for Git to figure out how to do that merger. Sometimes a merge can fail, in which case a merge conflict will appear. This basically happens when you ask to do a merge, Git tries to do it, but then it realizes it doesn't know how. So it's going to ask you to figure out how to do that merge. And then you're going to commit your changes. What does that look like? So I'm going to check out that branch, props 6 and 8. And then I make an edit to that branch. So in one of the parts of that problem, I attempted a solution. So I made an edit, I committed it, and then I try to do a merge with the main branch, which would try to get all the differences that appear to the main branch into this new variant of the product, but only the changes that are kind of in common between the two. So it wouldn't have gotten rid of all the new stuff that I added to that variant. But we try to do this merger and it fails. And what ends up happening is Git goes into the file, it identifies the lines where a conflict happened, and it inserts some stuff to indicate where the conflict was and what versions came from where. So in this case, it shows you some metadata. You see head is what we've currently checked out. And at the bottom we see main, which is the branch we were merging from. In between those equal signs and that bottom line main, that's all the stuff that was in the main branch. And the stuff in between those equal signs and that line that says head, that's the stuff that was in the branch that we currently checked out. One way or the other, we need to edit this file, resolve the problem ourselves, and then we're just going to make a new commit, and then we're done. So in this case, my resolution is I'm going to delete the lines that I added because this is the stuff in the main branch is a better solution. So I'm going to keep the stuff in the main branch. I'm going to delete the stuff that was in my personal branch in this variant. I'm also going to delete those like lines that say head and main and those equal signs. I'm going to delete that too. That was all inserted to indicate there was a merge conflict. So I delete all that stuff. This is now what the project should look like. And then I add it, and I commit it, and then I push. So that I've resolved the merge conflict. So that's all here's the summary of the branch management stuff. There's a tear sheet at the very end of this presentation that should be a cheat sheet that includes some of these common commands. So wrapping up, why am I talking about this? I think that Git is an important part of making research reproducible. Because the truth is, as a research project carries on, things are going to change. You're going to change the data as data comes in or as data gets updated. Maybe you discovered that something that was missing data before, well, actually we fat-fingered some process and we actually did manage to get that run. So we should update the data set. So the data changes. The statistician comes in and tells you made a whole bunch of analytical mistakes and tells you how to fix it. So you're going to change the analysis. So everything is changing. And as things change, you need to keep a record of how the data and the analysis are evolving over time in case you need to go back in time and explain why things are different. Often people are sharing the results of their work in intermediate phases. They're telling their supervisors, maybe they're giving their sponsor a sneak peek or something like that. This is what we've currently got. But but things are going to change, and you need to have a record so that you can see how the data and how the analytical methods produce the results that you're looking at any given point in time. And you really don't want to have to do that by hunting files down. You would rather have a process that's keeping track of this work. Git is a very, very powerful tool. It is powering massive software projects. In many ways, the reason why I'm talking about Git is because I know enough about Git to be somewhat productive with it. I am conversational in Git, but not fluent. Right? And I would say that a software developer at Amazon or whatever, they're going to know way more about Git than I do. But I know enough that I can give this talk and tell you how to make a merge and make a commit. But I have had Git do some really useful work for me. I have some stories for these. These are the commands that I would love to talk about, but I don't have time to. One is git grep. Let's suppose that at one point in time there was a variable in your project at some point in time, but you don't remember when or where. You can use git grep to search the entire history of your project for that variable. Everything. So from the moment you created it, or like this line appeared in a data set and you can't remember where or when, you can use git grep to find it from all versions of the data set. So it searches everything. Or those commits. You probably would imagine that there's probably a commit that might represent what you shipped on a December 7th. And like you actually went and delivered a presentation. This was the version of the data that you used at that time. And then this was the version of the data that you presented before Congress or something. I don't know. It would be nice if it were easier to reference that version of the data set or that version of the product without having to remember a 7-character string. There is a command called git describe where you can actually give an informative name to a commit to make it easier to find those really important commits. Git bisect. Oh wait, before I talk about Git bisect, there's Git Stash. If you wanted to do a Git reset, but you don't want to lose all your work, you want to very quickly save it, you can use Git Stash. Now Git bisect I've used once in my life, and I will remember it forever because it really saved me. Do I have time to tell a story? All right, so here's the story. I was doing my thesis work, and as I mentioned before, there were these simulations that I was using R, and I was also using C++ because some of these computations were rather rough and took a long time. It was a rather involved project from that stance, and I was using Git to keep track of it. It had a lot of these simulations I had to run on a supercomputer, and they would take even weeks to run on the supercomputer. Something that I'm not really hearing a lot of in the conversation about reproducible research, but features prominently in this story, is the concept of unit testing, where you write out these tests for segments of code to say, when this code runs with this input, this is the output I expect. Right? I expect this code to do this, and this code to do this, and this code to do this. So you write out these unit tests, and you can automatically run these unit tests to make sure that the code runs as you think it's supposed to run. Right? So I was doing this work. I was doing it on my laptop at home, and I had these unit tests that would automatically run whenever I created the package that corresponded to this project. And one day, I take all the work that I've been doing for several weeks, and I put it on the supercomputer, and I tell it to create the package, and all of a sudden, all of these tests that I had written started failing. And basically what these tests were doing was they were checking that when I input some numbers that I got some numbers out, and the numbers that started coming out were very different. It was a numerical difference, but not in like the 3rd or 4th or 9th or 10th decimal place, like in the ones place. So very significant numerical differences. And this is a moment where there's one of these days where you fall off your bike and you're a little banged up, but you're okay. And then you look at your helmet and you realize your own mortality. And this was one of those moments because I was like, oh my gosh, if I had not, there was no error. Nothing ever threw an error, nothing ever threw a warning that something was wrong. So the reason why I discovered there was a problem was because I had unit tests that checked that things were functioning as properly. And that error did not happen on my laptop. There was no error on my laptop, but there was on the supercomputer where I was doing all my work. And these were computations that were rather involved, so it's not obvious that it's an error either. It's not obvious that one number is right and one number is wrong. And these are computations that will take weeks to do. And nothing will ever tell me that anything is wrong. And I will just look at the results of those computer experiments and say, wow, that's what came out? Huh, that's disappointing. So this is the moment where it's like, if I had not written those unit tests, I would have never known anything was wrong, and I would have shipped it. And if I hadn't noticed it before I ran that code, even if I did find out something was wrong, which I wouldn't have, there was no way to know, it would have taken me weeks to redo it. Okay, so that's all well and good, but how did I fix the problem? How did I even find what the problem was? Because it sounds like a very, very subtle problem, doesn't it? Well, this is where Git bisect came to my rescue. Because I was like, okay, this command isn't working. Right now, my project doesn't work, but was there ever a point where it did? There was a point where it did. There was a point where the unit tests passed. So once I was able to find the current bad commit and the good commit, Git bisect would check out commits in between and say, hey, is this commit good? And then I'd run everything again, and it's like, no, that commit is bad. What about this commit? I run everything again. No, that commit is bad. What about this one? I run everything again. Oh, this commit is also good. Okay, what about one in between those two? And then you just have this process where it's bisecting, it's doing this logarithmic search until it found the first bad commit. And I was able to see, what did I do in that commit that caused a problem? The answer was that in C++, you had to put namespaces associated with functions, and I took out the namespace that was associated with some of the square root functions or the absolute value functions. So it resulted in an ambiguity in what function should be used. My laptop answered one way, and the supercomputer answered a different way. And Git helped me find that problem. So very, very hard to find. So I used that once, and I will always remember it. So, all right, here's a cheat sheet. This is what you print out and put on right behind your laptop when you're doing your work. And that's it. So I guess I'm ready for your questions now.
Do you have a recommended reference for Git?
Unfortunately, I do not, because I just do the bad thing where I go to Google and I ask for help.
There may be all kinds of fantastic.
I have a book called the Git Handbook on my desktop, and also but it's just like, okay, here's like a command, it does this. But towards the beginning of this, let's see, going back.
There's a free PDF called Pro Git, which is very good.
I think that's actually what they're recommending right here. Well then, so I mean, that's what Git's recommending. So this is the official website for Git. So that might mean something. So Matt, what's up?
Just my favorite reference is Happy Git with R. It's a Jenny Bryan book. So if you're using R with Git, it's an excellent resource from everything from getting started to using it in your workflow. That's another reference.
Yeah, and by the way, I didn't use a GUI, but it is definitely worth mentioning that there are graphical user interfaces for Git, and also Git is extremely popular. So programs such as RStudio have ways to integrate Git into them so that you can do some of this commit process yourself in RStudio. I don't use it. I'm perfectly happy with writing the commands because I don't think it takes very long myself. But some people may like that. Some people use that, and if that's what works for you, then you're welcome to use that. So
you can import a project from GitHub into R using just import URL.
Yeah, RStudio has a lot of stuff that for project management. A lot of people like that. I use Vim. For some people, that tells you all you need to know. So, what?
You don't look old
Oh, I love Vim. Vim is awesome, but that probably tells you how much I like who you're dealing with. So it's like, okay, some people really like that, and they're okay. So, anything else? Are we good? Are there any questions in the chat? Oh, there are a lot of questions in the chat. Shoot. But there's another question in the room.
Yeah, so Jupyter.
Yeah,
Jupyter notebooks,
yeah.
not plain text.
GitHub is able to handle them well, apparently.
Yeah, so is tracking, right? So it's not plain text, it's tracking them with Git. Presumably, I just didn't know if you had come across any solutions to that. Yeah, I mean, yeah.
I don't use I don't use Jupyter notebooks that much myself. I know that people upload their Jupyter notebooks onto GitHub, and GitHub renders it very nicely, so it must play with it nicely. I mean, it won't tell you what's changed in between notebooks if it's just a binary file, but it can still track it. So it's just copying the whole file. I would imagine that the notebooks themselves are not very big, and for that matter, space is really cheap anyway. So unless you're copying, unless you're like got these gigabyte size binary files, most of the time no one's going to care. These aren't the days where megabytes came in disks this big, and they cost $5,000. Oh, someone asked if there's a passcode to download the materials for this session. Oh wait, no, that's something else. That's the past session. What's actually corresponding to what we just talked about now?
There was one question in the chat that was clarifying the references. Oh. And then there's another question. So John pointed out earlier that the Control-V issue that you were discussing in the terminal, apparently, according to Wikipedia, can be traced to a VT100 or a similar device. Really? Apparently, I don't know what that is.
I know that most terminals just don't like Control-V. This is not just like the bash terminal. Terminals in general don't like it. I think that's because Control-V means something else when you're working in a terminal environment, so they don't like you to use that. I know definitely Control-C doesn't mean copy. It means like kill the process. So, that's the primary reason why. But if you're not used to a terminal, and even if you are used to a terminal, it's so instinctive to type Control-V that it's something to watch out for.
A lot of the newer ones now want you to hit Control-Shift-V.
Yeah, the Control-Shift-V work. Actually, in that terminal, Control insert is what you use to paste. But one way or the other, Control-V isn't it. It might be Control-Shift-V. So, anything else? Well, I guess we're 17 minutes before 5, so I guess we're good. Thank you all for coming.